Somewhere in the last century, humanity quietly decided that reaching other stars was a matter of time. The rockets would get faster, the engines would get better. Eventually, some generation would look back at us the way we look back at people who thought the Atlantic was uncrossable. It felt like the natural arc of things. We went from horse carts to orbital spacecraft in about 60 years. The assumption was that the stars were simply next. That assumption is wrong, and the reason it is wrong is not what most people expect. The barrier between us and the nearest star is not a funding problem. It is not a political will problem. It is not even a materials science problem waiting on the right alloy or the right rocket design. The universe placed something between us and every other star that sits in a completely different category from any obstacle humanity has overcome before. These are not engineering problems, they are physics problems, and that difference is the most important distinction in this entire conversation. Engineering problems get solved. Given enough time, enough money, enough clever people staring at the right diagrams, engineering problems eventually fall. Physics problems do not work that way. Physics problems are not waiting for a breakthrough. They are features of reality itself, baked into the structure of space and time and matter at the deepest level we know how to describe. When a physics problem says no, it does not mean not yet. It means the universe was built in a way that does not permit the thing you are trying to do. What follows is a walk through the specific barriers standing between humanity and interstellar travel. Not a single wall, but several. Distance so extreme that the numbers stop meaning anything to the human brain without careful translation. Speed limits written into the geometry of space-time by Albert Einstein more than a century ago. Limits that have never bent for anything, anywhere, under any conditions we have ever observed. Energy requirements so staggering they dwarf the output of entire civilizations. Radiation environments that treat the human body as a target. Biological systems that evolved for one specific planet and begin falling apart the moment they leave it. And theoretical escape routes. The wormholes and warp drives that fill science fiction, which turn out on inspection to require things the universe simply does not appear to contain. None of these barriers is a rumor. None of them rest on shaky science or pessimistic assumptions. Each one emerges from the same physics that built the stars themselves, the same equations that predict nuclear reactions and satellite orbits with complete accuracy. They have been tested. They have held. Each one is a wall the universe built on purpose, and none of them care about our ambitions. The closest star to our Sun is a dim red dwarf called Proxima Centauri, and it sits roughly 25 trillion miles away. That number is almost useless on its own. 25 trillion is too large for the human brain to hold in any meaningful way. So start smaller. A light year, the unit astronomers use to describe these distances, is not a measure of time, even though it sounds like one. It is a measure of distance. Specifically, it is the distance that light travels in a single year, moving at 186,000 miles per second through empty space. That works out to roughly 5.88 trillion miles. Proxima Centauri sits 4.24 light years from our Sun. Multiply 5.88 trillion by 4.24, and you arrive at approximately 25 trillion miles away. Numbers at that scale stop meaning anything to most people. So here is a different way to see it. Imagine shrinking the solar system to something you could walk across. Place the sun at the center of New York City, a basketball sitting on the pavement. On that same scale, Earth is a small marble roughly 26 yards away. Neptune, the outermost major planet, is nearly half a mile from that basketball. The entire solar system, everything we have ever visited with a spacecraft, fits inside a radius of less than a mile. Now place Proxima Centauri on that same scale. The nearest star, reduced by the same factor, is another basketball sitting somewhere in Los Angeles. 4,000 miles away from your basketball in New York, that is the gap between our sun and its closest neighbor, compressed into a model where Earth is a marble and the entire outer solar system is less than a mile wide. The distance is not exotic or abstract. It is the actual texture of the universe. And Proxima Centauri is the closest one. Beyond Proxima, the distances compound quickly. Alpha Centauri A and B, the two sun-like stars that form a binary system in the same general neighborhood, sit about 4.37 light-years out. Barnard's star, the next closest, is nearly 6 light-years away. Sirius, the brightest star in the night sky, burns at roughly 8.6 light-years. These are the neighbors. These are the stars so close by cosmic standards that they practically share our backyard. And the nearest among them still requires a journey of 25 trillion miles. The stars most people can name are not nearby at all. Betelgeuse, the red shoulder of Orion that has captured so much attention, sits roughly 650 light-years from Earth. Rigel, the blue supergiant at Orion's foot, is about 860 light-years out. Deneb, one of the brightest stars visible from the northern hemisphere, may be somewhere between 1,400 and 2,600 light-years away, so distant that astronomers still argue about the exact number. The light leaving Deneb tonight will still be traveling when civilizations we cannot imagine have risen and fallen on this planet. Step back further, and the numbers collapse into something that no longer resembles anything human. The Milky Way, our home galaxy, the structure our sun belongs to, is roughly 100,000 light-years across. The distance from one edge to the other, measured in the same units as that 4.24 light-year gap to Proxima, is 100,000 times larger. We sit about 26,000 light-years from the galactic center, somewhere in a quiet spiral arm. To cross our own galaxy at the speed of light would take 100,000 years, and the Milky Way is not a large galaxy. The Andromeda Galaxy, the nearest large spiral galaxy to our own, sits 2.5 million light-years from Earth. On a clear autumn night, away from city lights, you can see it with the naked eye, a faint smear of light in the constellation Andromeda. What you are seeing is not a star. It is an entire galaxy of 1 trillion stars, and the light entering your eye left that galaxy 2.5 million years ago, when the ancestors of modern humans were still using stone tools on the African savanna. That light has been crossing empty space since before our species existed, and Andromeda is considered a local neighbor. The observable universe extends roughly 46 billion light-years in every direction from Earth. It contains an estimated 2 trillion galaxies. These are not numbers that carry useful meaning at human scales. They are numbers that simply tell you the scale is wrong for us. Everything biology shaped us to understand, distance, time, travel, operates at a scale the universe does not share. There is something worth sitting with here. When you look at the night sky on a clear night, every star you can see with the naked eye is part of our own galaxy. None of them are in other galaxies. All of them are within a few thousand light years at most. The farthest stars visible without a telescope are perhaps 4,000 or 5,000 light years away. The closest is 4.24 light years. That entire range, from Proxima Centauri to the faint edge of what your eye can detect, represents a tiny local bubble inside a galaxy that is itself a tiny speck inside a universe containing 2 trillion more. And inside that bubble, every single point of light is separated from us by a distance measured in trillions of miles. Not hundreds, not thousands, trillions. The universe does not grade on a curve. It does not offer a nearby star just a few billion miles out, reachable on timescales that make sense to a civilization with a few centuries of technology. The gaps between stars exist at a scale that makes our solar system feel like a room, and the nearest star feel like a destination on another continent, reachable only by a mode of transport that does not exist and may never exist. Every single one of those points of light in the night sky is separated from us by a gulf that our fastest machines have never come close to crossing. Voyager 1 is the farthest human-made object ever launched, and right now it is moving at roughly 38,000 miles per hour. That number sounds fast. It is fast by any standard a human being encounters in daily life. A commercial airliner cruises at around 575 miles per hour. A rifle bullet travels at roughly 1,700. Voyager 1 is moving more than 20 times faster than a bullet, and it has been doing so continuously since 1977. The engineers who built it did something genuinely extraordinary. And yet, against the distances described in the previous section, 38,000 miles per hour is essentially nothing. Here is what that speed actually means when you point it at the stars. Proxima Centauri sits roughly 25 trillion miles away. At 38,000 miles per hour, Voyager 1 would need approximately 73,000 days, not 73,000 months, years. Agriculture is roughly 12,000 years old. The last ice age ended around 11,700 years ago. The entire recorded arc of human civilization, from the first written symbols in Mesopotamia to the present day, spans maybe 5,500 years. Voyager 1, traveling at its current speed toward Proxima Centauri, would still have 67,000 years left to go. The civilization that launched it would have had time to rise and collapse a dozen times before the probe arrived. Voyager 1 represents roughly 0.0057% of the speed of light. That fraction is so small it barely registers. You could double that speed, triple it, multiply it by 10, and you would still be nowhere close to what the journey requires. This is not a gap that incremental engineering improvements will bridge. The Parker Solar Probe does better. It is currently the fastest human-made object ever measured, achieving speeds near 430,000 miles per hour at its closest approach to the Sun. That is more than 11 times faster than Voyager 1. The engineers behind it used a technique called a gravity assist, swinging the probe around Venus repeatedly to accelerate it deeper into the Sun's gravitational well. The result is a spacecraft moving at a genuinely staggering velocity by human standards. At 430,000 miles per hour, you would cross the continental United States in about 20 seconds. At 430,000 miles per hour, the trip from Earth to the Moon would take roughly 34 minutes. Those are numbers that begin to feel almost incomprehensible. they are still 0.064% of the speed of light. At that speed, the journey to Proxima Centauri would take around 6,300 years. Civilizations would rise and fall. Languages would appear, evolve beyond recognition, and die. The probe launched by one version of humanity would arrive to a version of humanity that might share almost nothing with the one that built it, assuming any version survived at all. New Horizons, the probe that gave humanity its first close look at Pluto in 2015, is traveling at about 36,000 miles per hour on its way out of the solar system. A similar calculation puts its arrival at Proxima Centauri at roughly 78,000 years from now. 3 probes, 3 engineering achievements that genuinely pushed the boundaries of what humans have managed to build, and not one of them is remotely competitive with the distances involved. The shortfall here deserves to be stated plainly. To reach Proxima Centauri within a single human lifetime, roughly 80 years of travel time, you would need to be moving at something approaching 3% to 5% of the speed of light, depending on when you want to arrive and whether you care about decelerating at the other end. That works out to somewhere between 20 million and 33 million miles per hour. Voyager 1 is moving at 38,000. The gap between where human engineering currently sits and where it would need to sit is not a factor of 2 or 5 or even 100. It is a factor of roughly 500 to 900. 500 times faster than the fastest sustained speed we have ever achieved for an outbound spacecraft. There is an analogy that captures this more viscerally than the raw numbers do. Imagine the journey to Proxima Centauri as a drive across the United States, roughly 2,800 miles from New York to Los Angeles. Voyager 1's speed, scaled to that trip, represents having traveled about 16 feet. Not miles, not blocks. Feet. You are still in the driveway. The Parker Solar Probe, the fastest thing humanity has ever made, gets you perhaps 150 feet down the road. You can still see the house. Los Angeles is still a continent away. What makes this sobering rather than simply discouraging is that it reveals something about the nature of the problem. These probes were not slow because the engineers were unambitious or underfunded. Voyager 1 used gravitational assists from Jupiter and Saturn. The Parker Solar Probe uses repeated Venus flybys and the Sun's own gravity. These missions extracted every advantage the solar system's geometry offered. The speeds achieved are close to the practical ceiling for what conventional propulsion can do within a reasonable mission budget and mass. And that ceiling is about 0.06% of the speed of light. What would it take to do better? To reach 1% of light speed, roughly 6.7 million miles per hour, you need an entirely different category of propulsion. Nothing burning chemical fuel gets you there. Nothing relying on gravity assists from planets in our solar system gets you there. You need something that does not currently exist in any operational form, and possibly something that pushes against limits more fundamental than engineering. Before you can ask what kind of engine would get you there, you have to understand what fast enough even means in a universe this large. In 1905, Albert Einstein published a paper that quietly made interstellar travel impossible, although it would take the world several decades to fully absorb what he had done. The paper was called On the Electrodynamics of Moving Bodies. It was not long. It contained no new experimental data. What it contained was a set of mathematical consequences that followed from 2 simple postulates. And one of those consequences was this: the speed of light in a vacuum is the same for every observer. regardless of how fast that observer is moving. That single claim, followed to its logical end, restructures everything humanity thought it understood about speed, distance, and what it means to travel. Light moves at approximately 186,000 miles per second in a vacuum. That number is worth sitting with for a moment. In 1 second, light travels the distance between New York and Los Angeles roughly 62 times. In 8 minutes, it crosses the entire distance between the Earth and the Sun. In a little over a second, it reaches the Moon. These are not simply impressive numbers. They are the ceiling. Nothing carrying mass or information moves faster than this. Not because we haven't built a fast enough engine, not because the right fuel hasn't been discovered, but because space-time itself does not allow it. This is where most people make a category error. They hear the speed of light is the fastest anything can go, and they file it alongside other speed records, sound barriers, land speed records, things that humans once thought were impassable and then crossed. But the sound barrier was a technological limit. The speed of light is a geometric one. The difference is not a matter of degree. It is a different kind of thing entirely. Understanding this distinction requires recognizing that some limits emerge from insufficient technology, while others spring from the structure of reality itself. The sound barrier was a constraint imposed by the physics of moving through air at particular speeds. The speed of light is a constraint imposed by space-time itself. One could theoretically be overcome with better engineering. The other cannot be overcome, period. This difference shapes everything about how we must think regarding motion through the cosmos. Here is what Einstein's equations actually show. When an object with mass accelerates, it gains energy. That energy has an equivalent mass, and that equivalent mass itself resists further acceleration. The faster the object moves, the more its effective resistance to additional acceleration increases. At low speeds, this effect is so small it's unmeasurable. At 10% of light speed, it's minor but real. At 50% of light speed, you need significantly more energy per unit of speed gained than classical physics would predict. At 90% of light speed, the numbers become punishing. At 99%, they become nearly catastrophic. And as you approach the limit itself, the energy required to gain any additional speed approaches infinity, not a very large number. Infinity. The curve never reaches the speed of light. It only approaches it, asymptotically, forever. What this means in practice is that you cannot push through the light barrier the way a plane pushed through the sound barrier. The sound barrier required more thrust. The light barrier requires infinite energy. Those are not comparable challenges. One is an engineering problem. The other is a mathematical property of the universe that holds in every reference frame, in every corner of space-time, under every physical condition ever tested, and it has been tested. Particle accelerators around the world have been firing subatomic particles toward the speed of light for decades. At CERN, protons are accelerated to 99.99991% of the speed of light. The energy required to reach that final fraction of a percent is extraordinary. The protons never reach the limit. The closer they get, the more energy each additional increment costs. The equations predict this precisely, and the experiments confirm it precisely every single time. Special relativity is not a theory waiting to be overturned. It is one of the most tested and confirmed frameworks in the history of science. There is something worth understanding about where this limit comes from. The speed of light is not an arbitrary speed that happens to be very fast. It is a fundamental constant of space-time, the speed at which massless things travel through the vacuum. Photons move at this speed not because they are engineered for it, but because they have no mass. And in a universe where space-time has the structure it has, massless particles travel at sea. Massive particles cannot. They are, in a sense, stuck in a lower gear that they can approach but never close. The speed of light is the speed of causality itself, the rate at which cause and effect can propagate through the universe. To exceed it would not just be fast, it would be a violation of the causal structure of reality. This is the barrier that matters more than any other covered in this series. The distances are enormous, yes. The energy requirements are staggering. But those might seem, on the surface, like problems of scale. Build bigger engines, find denser fuel, wait for better technology. The light speed limit is different. It is not a problem of scale. It is a boundary condition on the universe itself, baked into the field equations that describe space-time, confirmed by every precision measurement ever taken, and carrying no asterisk that says, except with sufficient funding. Every other barrier we will discuss, the energy requirements, the radiation environment, the biology, operates inside this constraint. The light speed limit is the outermost wall, the one that was there before any of the others, and the one that no conceivable engineering improvement touches. The speed of light is not a record waiting to be broken. It is a feature of reality, as fundamental as the fact that time moves forward. If you somehow got a spacecraft up to 87% of the speed of light, something strange would start happening to time. Not metaphorically strange. Not strange in the way that long trips feel distorted. Strange in a precise, measurable, physical sense that Einstein worked out more than a century ago and that every experiment since has confirmed. Time on the ship would run at half the rate it runs on Earth. For every 2 years that passed at home, 1 year would pass on board. The clocks would disagree. The crew would age more slowly. This is not a malfunction. This is what space-time does. The effect is called time dilation, and it scales in ways that seem almost generous at first. Push the ship to 99% of light speed, and the ratio shifts to roughly 7:1. 7 years pass on Earth for every year the crew experiences. At 99.9% of light speed, the ratio reaches 22:1. At the most extreme velocities physically conceivable, the disparity grows so large that a crew could, in theory, cross hundreds of light years while aging only a handful of years themselves. The universe would age around them while they moved through it in something close to slow motion. On paper, this looks like a solution. It is not. Consider what it actually means for a mission to Proxima Centauri. The star sits 4.24 light-years away. At a speed of 99% of light, the crew's experienced travel time drops to something under a year. They leave Earth, spend less than a year in transit, and arrive. But back on Earth, 4.24 years have passed at minimum. That is the best case, at a speed that no propulsion system ever seriously proposed can reach. At more achievable fractions of light speed, the asymmetry becomes brutal. A ship traveling at 50% of light speed takes about 8.5 years to reach Proxima by Earth's clock. At 10% of light speed, which is still thousands of times faster than anything humanity has ever built, the journey takes 42 years each way. The crew might still be alive. The people who launched them probably would not be. Now push deeper into the galaxy. There are stars worth visiting that sit 50 light years away. there are potentially habitable systems at distances of 100 light-years or more. A crew traveling at 99.9% of light speed could reach a star 100 light-years out in about 5 years of ship time, but 100 years would pass on Earth. Everyone they knew would be dead. The civilization that launched them would have changed beyond recognition. The governments, the institutions, the families, the entire context of the mission would be gone. When the crew arrived and turned around and came back, another 100 years would pass on Earth. They would return home 2 centuries after they left, having aged perhaps 10 or 12 years. There is no communication across that gap in any useful sense. There is no mission control that means anything. There is no home to return to. This is the nightmare that time dilation actually produces. It does not allow interstellar travel in any human sense. It allows individuals to survive the journey while the civilization that sent them evaporates behind them. A round trip to anywhere significant becomes, by definition, a one-way trip into a future where nothing familiar remains. You could reach the stars. You could not bring back what you found to anyone who would remember why you went. Time dilation is not the only relativistic effect that punishes a fast-moving ship. There is also length contraction. From the crew's perspective, the distance to the destination shrinks as speed increases. At 99% of light speed, a 4.24 light-year journey compresses from their frame of reference to a fraction of that apparent distance. This is real, not an illusion. The geometry of space-time contracts along the direction of travel. But this changes nothing about the energy required to reach that speed, and it changes nothing about what is happening to time back home. The universe does not offer discounts. What it gives in one dimension, it takes in another. Then there is the mass problem. As a ship accelerates toward light speed, its relativistic mass increases. This is not the ship gaining physical bulk. It is a consequence of momentum and kinetic energy concentrating in ways the equations of special relativity describe precisely. The practical result is that the faster you are already moving, the harder it becomes to accelerate further. Each increment of speed toward the limit costs more energy than the last. At 87% of light speed, the ship's effective inertia has already roughly doubled from its rest value. At 99%, it is increased by a factor of 7. At 99.9%, by a factor of 22. The same factor, not coincidentally, that governs time dilation. The physics compounds in every direction simultaneously, and it always compounds against you. More speed requires more energy. More energy must be carried as fuel. More fuel means more mass. More mass makes acceleration harder. The relativistic mass increase adds another layer on top of all of that, making the final push toward meaningful fractions of light speed exponentially more punishing than any earlier stage of acceleration. What emerges from all of this is not a set of inconveniences. It is a structural rearrangement of what travel means. A mission that takes 10 years of ship time might consume a century of Earth time. A crew that returns has not come back from a journey. They have arrived in a future they had no part in building. The destinations that time dilation makes reachable within a human lifespan are still so far away that the world behind you has fundamentally transformed before you return, and the energy required to reach any speed where these effects become useful is so staggering that it amounts to its own separate wall, which the next section addresses directly. Relativity does not simply make interstellar travel difficult. It redefines the terms of what a journey is, what a destination means, and what it costs to come back. The mathematics of special relativity does not simply inconvenience interstellar travel, it restructures the entire meaning of what a journey would be. Before any of the other problems come into view, there is an energy requirement sitting at the base of interstellar travel that almost nothing else matters until you solve. The relativistic effects described before this point are real. Time dilation is real. The compounding mass problem is real. But all of those are downstream of something more immediate, something that hits you before you get anywhere near the interesting relativistic territory. To move a ship at a meaningful fraction of the speed of light, you need energy on a scale that the human mind was not built to process comfortably. Not energy that we haven't figured out how to generate yet. Energy that strains the physical limits of what any civilization on any planet can reasonably be expected to produce. Start with a ship. A crude vessel, reasonably sized, 1,000 tons. That is not enormous. A naval destroyer runs around 8,000 tons. A 1,000-ton spacecraft is modest, stripped down, carrying the bare minimum needed to keep people alive across interstellar distances. Now accelerate it to just 10% of the speed of light, not relativistic speeds, not the dramatic territory where time dilation starts reshaping the mission. Just 10%. A crawl by the physics that actually governs these distances. To get that ship to 10% of light speed, you need roughly 450 quadrillion joules of kinetic energy. The number is large enough that it requires its own explanation. Global human energy consumption across an entire year runs to about 580 exajoules. 1 exajoule is 1 quintillion joules. Humanity burns through 580 quintillion joules, keeping civilization running for 12 months. Every power plant, every vehicle, every factory, every data center, every light left on overnight everywhere on Earth, added together. Getting that modest 1,000-ton ship to 10% of light speed requires energy roughly equal to about 1/10 of 1% of that annual total. That sounds manageable. It sounds almost trivial. Here is what makes it devastating. That calculation assumes a perfect engine, 100% efficient. Every joule of stored energy converts with zero loss into forward motion. No heat escaping. No waste products. No friction of any kind. That engine does not exist. No real engine operates anywhere near that efficiency. Chemical rockets convert maybe 1 or 2% of their fuel's energy into actual thrust. Even advanced nuclear systems waste enormous fractions of the energy they produce. The moment you use a real engine instead of a theoretical one, the energy required climbs by factors, not percentages. Now push the speed upward. The relationship between velocity and kinetic energy is not linear. It is quadratic at low speeds and gets worse as you approach relativistic territory. Going from 10% of light speed to 20% doesn't double the energy requirement, it quadruples it. Going to 50% of light speed requires roughly 14 times the energy of the 10% case. At 90% of light speed, relativistic mass effects kick in hard, and the numbers become something that looks less like engineering and more like a cosmic joke. Each additional increment of speed costs exponentially more than the one before it. The curve bends upward and keeps bending, steeper and steeper, as you push toward the limit. None of that accounts for the return trip. Everything described so far is one way. A ship that accelerates to 10% of light speed and then keeps going. No stopping, no orbiting, no landing, no coming back. just a ballistic trajectory that carries whatever survives the journey past Proxima Centauri at a fraction of the speed of light, and then continues outward into the void. That is not a mission. That is a flyby probe at best. A crude mission that crashes through a star system at relativistic speed and cannot stop has not accomplished exploration. It has accomplished a very expensive demonstration of motion. To actually stop at the destination, you need the same energy again. Deceleration requires the same force as acceleration, applied in reverse. The ship that burned 450 quadrillion joules slowing down. And then, if anyone aboard wants to come home, if the mission is anything beyond a one-way voyage, the whole process happens again twice more. Accelerate back toward Earth, decelerate into our solar system. A round trip to Proxima Centauri at 10% of light speed, with proper deceleration at both ends, requires energy that exceeds the total energy humanity has produced across all of recorded history. Every fire ever lit, every barrel of oil ever burned, every nuclear reaction ever triggered, every solar panel ever built. Add all of it together, from the first time a human struck flint against stone to this moment, and it is not enough. What about more powerful energy sources? Fusion reactors, if humanity ever builds them, would be far more energy dense than anything we operate today. A working fusion plant converts mass to energy at roughly 1% efficiency via the mass-energy relationship. It is genuinely powerful. It is not powerful enough. The quantities of fuel needed, even for fusion, to meet the energy demands of an interstellar mission at meaningful speeds are so large that carrying them defeats the purpose. More fuel means more mass. More mass means more energy required to accelerate. The fuel itself becomes part of the problem, which is a separate nightmare covered next. The point here is simpler. The energy budget for interstellar travel, even at modest relativistic fractions, is not a challenge that better energy technology will quietly solve. It is a wall with a specific height, set by the laws of momentum and relativity, and every energy source we can identify, every one, falls short of that height by orders of magnitude. This is the energy wall. It sits at the beginning of every serious interstellar proposal. You cannot root around it. You cannot argue with it. The physics that sets the requirement is the same physics that built the stars. No civilization running on any energy source we have discovered or theorized can fuel an interstellar trip the way the physics demands it be fueled. In 1903, a Russian schoolteacher named Konstantin Tsiolkovsky wrote down an equation that has been quietly humiliating rocket engineers ever since. Tsiolkovsky was not building rockets, he was doing math. He wanted to understand the fundamental relationship between a rocket's speed, its exhaust velocity, and the mass of the propellant it burns. What he found was a clean, elegant equation. It was also, for anyone dreaming of reaching the stars, a catastrophe written in variables. The equation is not complicated. A rocket moves forward by throwing mass backward. The faster the exhaust leaves the engine, and the more of it you throw, the faster the rocket goes. That part is intuitive. The problem is what the math reveals when you push those numbers toward interstellar speeds. You do not need a little more fuel. You need an amount of fuel that makes the mission geometrically, physically, absurdly impossible. Here is how the feedback loop works. Say you want to reach a higher speed. You need more propellant, but that propellant has mass. That mass is sitting on your rocket from the moment of launch, and it has to be accelerated too, along with everything else. Accelerating it requires burning more propellant, but that extra propellant also has mass, which requires more propellant, which has mass. The equation is exponential, not linear, and exponential feedback in the wrong direction is one of the cruelest things in all of engineering. Physicists and aerospace engineers call this the tyranny of the rocket equation, and the word tyranny is not hyperbole. For chemical rockets, the tyranny is already apparent right here on Earth. The Saturn V, the most powerful rocket humanity has ever launched, stood nearly 363 feet tall and weighed about 6.5 million pounds at liftoff. The payload it delivered to the moon was roughly 100,000 pounds. That means roughly 98% of what left the launch pad was propellant and structure being burned away just to move a tiny fraction of the total mass. Getting a small spacecraft entirely free of Earth's gravity on a trajectory that leads out into deep space requires starting with something that is around 95% fuel by mass. And Earth's gravity is not even the hard part. The hard part is what happens when you aim those numbers at interstellar speeds. The best chemical propellants humans have ever developed produce exhaust velocities around 4.5 kilometers per second. 10% of the speed of light is about 30,000 kilometers per second. The ratio between those two numbers tells you immediately that something is broken. To reach 10% of light speed using chemical propulsion, the rocket equation demands a fuel-to-payload ratio that exceeds any physical quantity that has meaning. The fuel required would not merely outweigh the ship, it would outweigh Earth. It would outweigh the solar system. You run out of matter in the observable universe before you run out of fuel requirements. Chemical propulsion does not fail at interstellar speeds because the technology is immature. It fails because the physics of how chemical reactions release energy is fundamentally mismatched to what the rocket equation demands. Nuclear propulsion changes the numbers. A nuclear pulse drive, of the kind studied under Project Orion in the late 1950s and early 1960s, works by detonating a series of nuclear bombs behind the spacecraft and riding the shockwave. The exhaust velocities are dramatically higher than chemical rockets, and the energy density of fission or fusion reactions dwarfs anything chemistry can produce. Project Orion studies suggested that a large nuclear pulse vehicle could potentially reach speeds of 1 to 3% of the speed of light, given a sufficient supply of nuclear devices. That sounds promising until you do the travel time calculation. 3% of light speed to Proxima Centauri. The journey would take over 140 years. That is a generation ship problem, not a solved one. And the fuel mass required for Project Orion at those speeds was already staggering. The design studies called for thousands of nuclear bombs just for the propulsion sequence. Scaling further to reach even 5% of light speed pushes the fuel requirements back into absurdity territory. Ion drives approach the problem from a different direction. Instead of burning propellant chemically or in a nuclear reaction, ion drives strip electrons from atoms and accelerate those ions electrically to extremely high exhaust velocities. The efficiency is remarkable. The thrust is not. Ion drives produce accelerations measured in fractions of a millimeter per second. They are excellent for long missions within the solar system where small thrusts can accumulate over months or years. For interstellar speeds, the thrust is so low that reaching even a fraction of a percent of light speed would require running the engine for centuries, while simultaneously carrying more propellant than the drive could ever push to meaningful velocity. Efficiency and thrust are in tension, and interstellar travel demands both at levels ion drives cannot simultaneously provide. Fusion propulsion is often cited as the hope between chemical rockets and the more exotic proposals. Fusion reactions release energy far more efficiently than fission, and the exhaust velocities theoretically possible with fusion products are far higher than nuclear pulse designs. The problem is that controlled, sustained fusion for propulsion does not exist. We have not achieved it for power generation on Earth. Translating a technology we have not yet demonstrated into a propulsion system capable of reaching interstellar speeds involves compounding uncertainties that push the timeline well beyond any serious near-term projection. What every one of these systems shares is the same fundamental constraint. They all carry their fuel, and carrying fuel is what the rocket equation punishes. The only escape from Tsiolkovsky's equation is to find your energy somewhere other than the fuel tanks you launched with. That is not an idle thought. It points directly at the next class of proposals, the ones that try to leave the propellant behind entirely. Whether those proposals solve anything or simply trade one impossible problem for another is a separate question. Every propulsion system ever built or seriously proposed runs into this same wall, and the wall does not move. The most serious proposals for interstellar propulsion are not science fiction. They are real physics, worked out by serious people at serious institutions. These are not fringe ideas sketched on napkins. They come with mathematics, peer-reviewed papers, and in some cases, serious government funding. And every single one of them, when you press hard enough on the details, runs into a wall. Not a wall of ignorance, a wall of physics. Start with the oldest serious proposal on the list. Project Orion was a real program, funded in part by the United States government in the late 1950s and early 1960s, and its concept was genuinely audacious. You detonate nuclear bombs behind a massive pusher plate at the rear of the spacecraft. The shockwave from each explosion accelerates the ship forward. Repeat this hundreds or thousands of times and you can, in principle, reach a few % of the speed of light. The physics did not obviously forbid it. The problem was everything else. A crude Orion ship capable of reaching even 2 or 3% of light speed would require somewhere between a few hundred and several thousand nuclear warheads, depending on the design. The political obstacles buried the program long before engineering could, but set that aside entirely and accept the physics at face value. At 2% of light speed, the trip to Proxima Centauri takes roughly 200 years. The rocket equation's grip loosens slightly, but the destination is still centuries away. Orion is not a solution. It is a demonstration of how hard the problem actually is, even when you are willing to light off nuclear weapons behind your ship every few seconds. Ion drives represent a completely different philosophy. Instead of brute force, they use efficiency. An ion drive strips electrons from a propellant, usually xenon, and accelerates the resulting ions electrostatically to produce thrust. The exhaust velocity is dramatically higher than any chemical rocket, which means far better fuel efficiency by the numbers. The catch is thrust. Ion drives produce a force measured in millinewtons. A sheet of paper resting on your hand exerts more force than some ion engines at full power. They accelerate slowly over months and years, and they are excellent for missions within the solar system where time is available and the destination is reachable. For interstellar distances, patient acceleration over years might get a probe to somewhere around Voyager's current speed class, perhaps a bit faster with significant advances. That puts Proxima Centauri at roughly 70,000 years away. Ion drives are among the most elegant propulsion technologies ever built, and they are nowhere near sufficient. Then there is Breakthrough Starshot, and this one deserves more careful attention because it is the most credible near-term concept anyone has seriously proposed. The idea, announced in 2016 with backing from Yuri Milner and Stephen Hawking, is to sidestep the rocket equation entirely. Instead of carrying fuel, the probe carries a sail. A ground-based laser array pumps gigawatts of energy into that sail over a matter of minutes, accelerating a gram-scale spacecraft to roughly 20% of light speed. At that velocity, Proxima Centauri is a 20-year trip, but the engineering problems stack up fast. A laser array producing the required power output would be among the largest and most expensive installations humanity has ever built. Pointing that array with the precision required, holding a tight beam on a sail only meters across as it accelerates to a fraction of light speed, demands engineering tolerances that do not currently exist. The sail material would need to reflect the laser energy almost perfectly, while surviving an intense radiation and particle environment that would destroy any material we currently know how to make. And here is the part that stops many researchers cold. The probe has no way to slow down. It arrives at the Proxima Centauri system at 20% of light speed and flies straight through it. The entire encounter with another star system lasts a few hours. Whatever instruments the probe carries have minutes, perhaps less, to observe anything useful before the system vanishes behind them. You spend 20 years in transit and get a few hours of data. That is not nothing, but it is also not what most people picture when they imagine reaching another star. Antimatter drives occupy a category of their own, because on paper they are extraordinary. When matter and antimatter meet, they annihilate each other completely and convert their entire mass to energy. There is no more efficient fuel possible under the laws of physics. A kilogram of antimatter annihilating with a kilogram of ordinary matter releases energy equivalent to dozens of nuclear warheads. A sufficiently large antimatter engine could, in principle, reach a substantial fraction of light speed. The physics does not forbid it. The universe, however, is not cooperating with production. Producing a single gram requires more energy than a nuclear weapon, and years of continuous accelerator operation. For an interstellar mission, you would need kilograms, possibly tons. The gap between what we have produced and what a mission would require is not a factor of 10 or 100. It is closer to a factor of 1,000,000,000,000. That is not a manufacturing challenge that scales with investment. The infrastructure needed to produce antimatter at interstellar mission quantities does not exist and has no clear path to existing. The energy cost alone would dwarf the output of entire nations. What you find when you lay all of these proposals side by side is a pattern. Each one is serious, each one is grounded in real physics, and each one fails at a different point. One on thrust, one on fuel mass, one on pointing accuracy, one on production capacity, but all of them fail. The rocket equation pressure does not go away just because the concept is sophisticated. The energy requirements do not shrink just because the engineering is clever. Each one either cannot produce enough speed, cannot carry enough fuel, or requires resources so far beyond anything humanity could build that the gap is not a generation of progress away. It is an entirely different civilization's worth. The space between stars is not empty. This surprises most people when they first encounter it, because everything we know about interstellar space points toward vacancy, the vast, silent gulf between one star and the next. But that gulf is filled, thinly, almost unimaginably thinly, but filled. On average, you find roughly one hydrogen atom per cubic centimetre out there. Heavier molecules, ionized particles, traces of helium and carbon compounds, all moving slowly through the dark. By any standard a human laboratory would recognize, this qualifies as a vacuum more perfect than anything we can manufacture on Earth. A vacuum chamber in a physics lab holds far more material per cubic centimetre than the interstellar medium does. At the speeds any spacecraft has ever travelled, this poses no problem at all. You simply pass through it, and the particles pass around you, and nothing of consequence happens. The problem arrives when you try to go faster. At 10% of the speed of light, the physics changes in a way that is not intuitive. The hydrogen atoms are not moving any faster than they were before. The ship is. From the perspective of anything on that ship, each hydrogen atom sitting quietly in interstellar space is now incoming at 30,000 kilometers per second. That is not a gentle encounter. At that relative velocity, a hydrogen atom carries the energy of a particle accelerator beam. Your ship is not drifting through a thin gas anymore. It is flying into continuous particle bombardment, the same kind of bombardment that researchers on Earth use to probe the structure of matter inside enormous machines costing billions of dollars to build. Except on those machines, the collisions are controlled. On your ship, they are happening across every square centimetre of the hull, every second, for years. Push that speed to 20% of light, and the situation becomes catastrophic for any crew on board. The energy of each hydrogen collision scales with velocity in ways that compound against you. At 20% of C, every proton your ship strikes carries energy comparable to what you would find inside a major particle collider. The interstellar medium becomes, simultaneously, a radiation bath and something close to a sandblaster. The radiation dose accumulating inside an unshielded hull at that speed would be lethal within days. Not elevated cancer risk over decades, lethal within days. The ship would be delivering a fatal dose to its crew faster than most medical emergencies. Shielding is the obvious answer, and it is where the problem deepens rather than resolves. A thicker metal hull does not solve this. High-energy protons pass through metal. They interact with it, they fragment inside it, and those fragments produce secondary radiation of their own, which can be worse than the original bombardment. What you need is electromagnetic deflection, a magnetic field strong enough to push charged particles out of the ship's path before they reach the hull. This is theoretically possible. The engineering required to sustain a magnetic field of sufficient strength over the entire surface area of an interstellar vessel, continuously, for years or decades, represents a power draw and structural complexity that feeds directly back into every other problem the mission already faces. More power means more mass. More mass means more fuel. You already know where that leads. Physical shielding carries its own punishment. Any solid material placed at the front of a relativistic spacecraft will absorb impacts, and absorbing impacts at these energies means losing mass. The shield ablates. Particles strike, material is ejected, and the shield thins over time in ways that are difficult to model and impossible to stop without continuous replacement. Over a journey of 4 light-years, the cumulative erosion on a physical shield is not trivial. You are not protecting a ship against occasional debris. You are defending against an uninterrupted stream of high-energy collisions for the entire voyage. Then there are the dust grains. This is the detail that tends to stop the conversation cold. The interstellar medium is not just hydrogen atoms. It contains dust, silicate grains, carbon particles, small clumps of frozen molecules. Most of these are microscopic. A millimeter-scale grain is, by the standards of the interstellar medium, enormous. At 20% of the speed of light, a grain with a mass of 1 gram carries kinetic energy roughly equivalent to a nuclear weapon. Not a large one, but a nuclear weapon released against whatever part of your hull it happens to strike. The material blows through. There is no hull thick enough to absorb that cleanly and remain intact. The probability of encountering such a grain over 4 light-years is not negligible. The interstellar medium is not uniform. There are denser regions, dust lanes, molecular cloud boundaries. The path from here to Proxima Centauri does not thread through a perfectly mapped, perfectly clean corridor. You are crossing territory that has never been measured in the detail an interstellar mission would require. Even in the cleaner regions, the statistics over 4 light-years of travel through a medium containing dust at interstellar densities give you a meaningful chance of a catastrophic strike before you arrive. What makes this barrier different from the energy problem or the rocket equation is that it was never part of the conversation for most of the history of spaceflight. Slow spacecraft, the kind humanity has always built, simply do not experience it. Voyager 1 is passing through the interstellar medium right now. It does not matter. At Voyager's speed, individual hydrogen atoms are irrelevant, and the probability of a significant dust impact over any human-relevant time frame is vanishing. The interstellar medium only becomes a threat when you commit to the one thing you cannot avoid committing to if you want to reach another star in a human lifetime: going fast. Speed is the requirement, and speed is what turns a near-perfect vacuum into something that kills you. At low speeds, the interstellar medium is irrelevant. At relativistic speeds, it becomes one of the most hostile environments in the known universe. Beyond the heliopause, roughly 120 astronomical units from the Sun, the protective bubble our star has been blowing around us for billions of years simply stops. What lies beyond that boundary is not simply empty space. It is a kill zone, and it has been waiting there the entire time humanity has been looking at the stars. To understand why, you need to understand what the heliopause actually does. The Sun constantly streams charged particles outward in all directions, the solar wind. That wind pushes back against the interstellar medium, carving out a vast bubble of relatively calm space that contains our entire solar system. Inside this bubble, galactic cosmic rays are partially deflected. Not entirely, but enough. The magnetic field of Earth adds another layer on top of that, deflecting additional particles before they reach the surface. Life on Earth sits behind 2 separate shields, and most people have never had reason to think about either of them. Astronauts on the International Space Station are still inside Earth's magnetic field. They receive roughly 10 times the radiation dose of someone standing on the ground. 10 times sounds alarming, and it is monitored carefully. But ISS astronauts are shielded enough that career dose limits keep missions to manageable lengths. On the lunar surface, the picture gets worse. The moon has no global magnetic field and no atmosphere, so galactic cosmic rays and solar particle events arrive with much less interference. Apollo astronauts spent only days there. A lunar base would require serious shielding strategies just for permanent habitation within our own backyard. Now remove both shields entirely. That is what interstellar space looks like. Galactic cosmic rays are not the gentle radiation of a medical X-ray. They are atomic nuclei, protons, helium nuclei, and heavier elements, accelerated to enormous energies by supernovae, neutron stars, and other violent events scattered across the galaxy. Some of them carry energies that dwarf anything produced in particle accelerators on Earth. They travel at fractions of the speed of light. When one of these particles hits a human cell, it does not simply deposit energy the way a photon does. It tears through tissue in a straight line, ionizing everything along its path, snapping DNA strands, damaging the molecular machinery cells use to repair themselves. The body has repair mechanisms for radiation damage, and they work reasonably well at low exposure rates. But galactic cosmic rays in interstellar space arrive at a flux that overwhelms those mechanisms. Career dose limits for astronauts, the maximum radiation exposure agencies like NASA consider acceptable over a lifetime of spaceflight, would be exceeded within months in deep interstellar space, not years. Months. The cancer risk compounds with every passing week, but cancer is not even the most immediate concern. High-energy heavy nuclei, the iron and silicon cores that make up the heaviest fraction of cosmic ray flux, are particularly destructive to the central nervous system. Studies on animal subjects exposed to simulated cosmic ray environments have found measurable cognitive decline, impaired spatial memory, and behavioral changes from relatively short exposures. These are not theoretical projections. They are experimental results suggesting that the human brain, not just the body, is vulnerable in ways that accumulate faster than most people assume. There is also the solar particle event problem. These are bursts of energetic particles launched by solar flares and coronal mass ejections. Near Earth, they are dangerous enough to force astronauts to shelter in shielded modules of the ISS. The sun's influence weakens with distance. By the time you are beyond the heliopause, any large solar particle event still reaches you, but without the buffer of the heliosphere to absorb part of the flux. And no shelter is nearby. A major solar particle event striking an unshielded crew in interstellar space would deliver an acute radiation dose capable of causing radiation sickness within hours and death within days. The engineering response to radiation is shielding. This seems straightforward until you work through the numbers. Reducing galactic cosmic ray exposure to acceptable levels requires shielding equivalent to roughly 2 to 3 meters of water surrounding the crew habitat. Water is one of the better shielding materials available because of its hydrogen content. Hydrogen is effective at breaking up incoming particle cascades. 2 to 3 meters of water surrounding even a modest crew compartment represents hundreds or thousands of tons of mass. Feed that mass penalty back into the rocket equation discussed earlier, and the energy requirements for the mission climb sharply. Every solution to the radiation problem makes the propulsion problem worse. The two barriers are linked, and addressing one tightens the grip of the other. Some proposals suggest using the ship's own fuel as shielding, surrounding the crew with propellant tanks. This works while the fuel is present. As the ship burns through it during acceleration, the shielding thins. By the time the vessel reaches interstellar cruise speed, much of that protection is gone. The crew then travels for decades inside a much thinner shell, exposed to the full galactic cosmic ray environment. Other proposals involve magnetic shielding, generating a powerful magnetic field around the ship to deflect incoming particles the way Earth's magnetosphere does. The mass and power requirements for a magnetic field strong enough to meaningfully deflect high-energy cosmic rays at a ship scale are, again, enormous. The system would itself require substantial energy, feeding back into the propulsion budget, and would not stop the heaviest, most energetic particles regardless. There is no material that solves this cleanly. High-density metals absorb some radiation but also produce secondary particle showers. The incoming particle hits the shield and fragments into a spray of secondary particles that can themselves be damaging. The physics of shielding against galactic cosmic rays is not a problem where thicker material reliably means more protection. It requires a careful balance that at interstellar mission mass budgets becomes nearly impossible to optimize. The radiation environment of interstellar space does not respond to engineering creativity. It is a direct consequence of how the universe generates and accelerates particles, and it has been doing that long before biology existed. Suppose for a moment that all the engineering problems were solved: the propulsion, the shielding, the energy. Imagine a drive that accelerates a crude ship to something indistinguishable from the speed of light. No radiation damage, no rocket equation, no exotic matter required. Every barrier covered in the sections before this one, erased. The ship works. The crew is healthy. They are moving at the maximum speed the universe permits. What happens next is not a triumph. What happens next is a confrontation with something the engineering fixes cannot touch: the raw scale of the universe itself. The closest star to our Sun is Proxima Centauri. At the speed of light, you reach it in 4.24 years, one way. Alpha Centauri A and B, the two Sun-like stars in the same system, sit slightly farther out, 4.37 years at light speed. These are the nearest stellar neighbors our Sun has, and even at the physical maximum speed permitted by the laws of physics, a round trip to the closest one takes nearly 9 years. That is 9 years assuming you arrive, turn around instantly, and leave. No time to study the system, no time to look for planets up close. Just touch the edge of another star's gravity well and come home. Now push the question further. The nearest confirmed potentially habitable worlds around Sun-like stars sit tens of light years away. Tau Ceti, one of the more discussed candidates, is about 12 light years out. A round trip there and back, travelling at the speed of light, takes 24 years minimum. Kepler 442, which orbits a star with conditions closer to Earth's, is roughly 1,200 light years away. A round trip takes 2,400 years at the absolute physical maximum speed. Not with a slow rocket, not with current technology. At the speed of light, 2,400 years. The people who launched that mission would be dust long before it returned. Within 50 light years of Earth, astronomers estimate there are likely dozens of star systems with conditions that might resemble Earth's in some way. 50 light years sounds manageable until you do the arithmetic. A round trip to any of those systems at the speed of light takes a minimum of 100 years. Nobody who leaves on that mission comes back within a human lifetime. Nobody who funded the mission, trained the crew, or watched the launch is alive when the ship returns. Every single destination in what astronomers call our stellar neighborhood requires either a multi-generational commitment or a technology that exceeds light speed, which the universe has already forbidden. The numbers get worse quickly. The center of the Milky Way sits roughly 26,000 light-years from Earth. A ship traveling at light speed reaches it in 26,000 years. The return trip takes another 26,000. 52,000 years round trip at the fastest speed anything in the universe can travel. Time dilation would compress the crew's experienced time significantly. They might age only a few decades aboard the ship, but Earth would have aged 52,000 years while they were gone. Whatever civilization launched the mission would be unrecognizable by the time any signal came back, let alone the crew. Human civilization as we currently understand it is roughly 10,000 years old. A round trip to the galactic center takes 5 times that span, even at light speed, measured in Earth time. The Andromeda Galaxy is the nearest large galaxy to our own. It sits 2.5 million light-years away. A ship moving at the speed of light takes 2.5 million years to reach it. The return journey takes another 2.5 million years. Everyone aboard that mission would return to a solar system that has aged 5 million years. The entire evolutionary history that separates modern humans from our early hominid ancestors fits inside that window several times over. Homo sapiens as a species is perhaps 300,000 years old. Whatever biological thing climbed back out of that ship after 5 million years of elapsed Earth time would be returning to a planet it had no conceivable connection to. And that is assuming Earth still exists and is still inhabited, which over a 5 million year window is not guaranteed. There is something worth sitting with here. These are not distances that a faster ship can solve. The problem is not that we lack a sufficiently powerful engine. The problem is that the universe placed stars at distances measured in years of light travel, and biology runs on timescales measured in decades. Those two facts do not reconcile. A human lifetime is roughly 80 years. The nearest star systems that might hold anything interesting take hundreds or thousands of years to visit, even at the ultimate speed limit. The mismatch between the timescale of biology and the timescale of cosmological distance is not a small gap that clever engineering narrows. It is a structural feature of the universe, as fixed as the distances themselves. What this means, practically, is that even a civilization with a perfect drive, frictionless, efficient, capable of genuine light speed, would still find the galaxy effectively partitioned into isolated neighborhoods. Individual star systems, perhaps small clusters of nearby stars, connected to each other with immense difficulty and disconnected from anything farther away by spans of time that exceed the length of recorded history many times over. The dream of an interstellar civilization, ships moving between stars the way ships once moved between continents, depends not just on solving the physics of propulsion, but on somehow compressing distances the universe has no interest in compressing. The universe is not large the way a country is large, or even the way an ocean is large. It is large in a way that makes the concept of travel between stars almost meaningless at human timescales. If you cannot get there in a human lifetime, the obvious response is to build a ship large enough to sustain a civilization that will outlast the journey. The idea is old. Science fiction writers were sketching it in the 1940s. The concept is straightforward enough. If the distance is too vast for one human life, send enough humans that the mission survives across many lives. Build a vessel so large and so self-sufficient that generations are born, live and die aboard it, and eventually Centuries later, the descendants of the original crew arrive at another star. It sounds like a solution. It is not. What it actually is a transfer of one impossible problem into several different impossible problems. Start with the biology. A generation ship carries a founding population, and that population has to remain genetically viable across hundreds of generations of breeding in an isolated, closed environment. This is not a small constraint. Population geneticists have studied this carefully. The number most commonly cited as the minimum viable founding population for a multi-generational voyage is somewhere between 2,000 and 10,000 individuals. Below that threshold, inbreeding accumulates over generations faster than random mutation can refresh the gene pool. Rare recessive disorders become common. Fertility drops. The population grows increasingly fragile in ways that compound across centuries. 2,000 people is not a crew. It is a small city. You are not building a spacecraft at that point. You are building a habitat that flies, with farms, water treatment, medical facilities, schools, manufacturing, and the full social infrastructure that any concentrated human population requires to function. The engineering mass of such a vessel is not in the same category as anything humanity has ever attempted to put into space. Even if you solve the engineering, the genetic problem does not fully disappear. Carefully managing reproduction across centuries requires institutional continuity that history gives us almost no reason to expect. The Roman Empire did not last 400 years in stable form. Neither did the Han Dynasty, the Ottoman Empire, or virtually any complex human institution you can name. You are asking a society sealed inside a metal hull, cut off from every external influence, to maintain rigorous genetic record keeping and reproductive planning across a time span longer than most civilizations have ever survived. The odds are not favorable. Then there is the question of consent. The founders of the mission chose this. They understood what they were signing up for, at least in broad terms. Their children did not choose it. The people who actually walk onto the surface of another world at the end of this journey, if it ever ends, will have been born into confinement, lived their entire lives inside the same walls, and been handed a mission by ancestors they never met. They had no vote, no exit, no alternative. Whether it is ethical to condemn people to lives they cannot escape in service of a goal they did not set is not a question physics answers. It is a question moral philosophy has wrestled with for centuries without resolution. The generation ship does not avoid this question. It makes it unavoidable. The social dynamics of a closed society with no exit are also not reassuring. History offers some relevant data. Small isolated communities, island populations, polar expeditions, long submarine deployments consistently develop elevated rates of conflict, rigid social hierarchies, and eventually fracture. These are populations with communication links to the outside world, with the knowledge that the isolation is temporary, with legal and cultural frameworks imported from larger societies. A generation ship has none of those stabilizers. The people aboard it are, after the first few years of travel, beyond any reach of the civilization that launched them. Light-speed communication delay grows to years and then decades. There is no authority that can intervene, no court of appeal, no external culture to borrow norms from. Whatever social order develops aboard that ship, for good or ill, is the only social order that exists. And whatever political dysfunction or violence or collapse happens inside it, there is no help coming. This is not speculation designed to be pessimistic. It follows from what closed system sociology actually shows. A society with no exit and no external input is not a stable equilibrium. It tends to drift toward authoritarianism, because concentrated populations in resource-constrained environments with no external check on power tend to produce leaders who consolidate it. Or it fractures into factions, because humans in permanent close quarters without the release valve of being able to leave tend to develop intense in-group conflicts. Either outcome is catastrophic for a mission requiring centuries of coordinated behavior. And then there is the matter of resources. No closed system is perfectly efficient. Every atmosphere recycling system loses trace amounts of gas. Every water reclamation system leaves behind accumulating contaminants. Every food production cycle has waste streams. In the short term, these losses are manageable. Over 50 years, they require careful engineering. Over 300 years, the compound losses from imperfect recycling become existential. A leak rate of 0.5% per decade in a critical resource sounds trivial. Run it forward 3 centuries and you are in crisis. The engineering of a closed life support system that maintains reliable function across that time span, with no external resupply and no replacement parts that were not manufactured aboard the vessel, is a challenge that makes the propulsion problem look modest. What emerges from all of this is that the generation ship concept does not circumvent the difficulty of interstellar travel. It relocates it. The physics problem, too far, too slow, too long, is answered with an object that is theoretically large enough and long-lived enough to absorb the time. But absorbing centuries of travel time inside a sealed human society introduces problems of genetics, consent, social stability, and resource management that are, in many ways, harder than the physics. Physics, at least, follows predictable rules. A generation ship does not solve the problem of interstellar travel. It trades the physics problem for a human one. And human problems have a worse track record of being solved. If you cannot solve the time problem with speed, the next obvious move is to make the passengers not experience the time. Put the crew to sleep. Freeze them. Wake them up at the destination, decades later, none the worse for it. This idea has appeared in science fiction so often that it feels almost inevitable. A solved problem waiting for the engineering to catch up. The biology says otherwise, and the biology is not being modest about it. The first thing worth understanding is what hibernation actually is. Animals hibernate, bears do it, ground squirrels do it. The Arctic ground squirrel is the most extreme case anyone has found. It drops its body temperature to roughly 27 degrees Fahrenheit, just below freezing, and stays there for months. Researchers have studied this animal extensively because it does something no other mammal does. Its cells tolerate conditions that would kill almost anything else. But here is the critical detail. The Arctic ground squirrel is not in suspended animation. Its heart still beats. Its brain still cycles through activity. Its metabolism has slowed to a fraction of its normal rate, but it has not stopped. The animal is running in low power mode, not switched off. The gap between what the ground squirrel does and what an interstellar mission needs is not a gap of engineering sophistication. It is a gap in the fundamental biology of what mammalian cells can survive. Human cells are mostly water. When water freezes, it does not freeze uniformly. It forms crystals, and those crystals have edges, sharp ones. At the cellular level, ice crystal formation is essentially mechanical destruction. The crystal edges shred lipid membranes, puncture organelles, and tear apart the internal architecture that keeps a cell functioning. A cell that has been frozen and thawed in this way is not a sleeping cell, it is a damaged one. In many cases, it is a dead one. This is not a temperature calibration problem. It is a consequence of the physics of water at low temperatures, and water is not optional in human biology. Cryoprotectants exist to address this. These are compounds, something like biological antifreeze, that get absorbed into tissue before freezing and disrupt ice crystal formation. They work. At small scales, they work remarkably well. Researchers have vitrified individual organs. Sperm and embryos have been frozen and successfully revived for decades. Thin tissue slices survive the process under laboratory conditions. The technology is real, and it is not nothing. The problem is scale. A whole human body contains roughly 37 trillion cells. Getting cryoprotectants distributed evenly through that tissue in the right concentrations, fast enough to prevent crystal formation everywhere simultaneously, is a problem that no one has solved. The largest successfully vitrified and recovered structures are still measured in millimeters. A human brain alone is roughly 1,400 grams of extraordinarily dense, extraordinarily complex tissue. No large mammal has ever been frozen and successfully revived. Not one. The brain deserves its own moment here. Every memory you have, every skill, every aspect of personality and cognition is encoded in the pattern of synaptic connections between roughly 86 billion neurons. That pattern is unimaginably intricate. A single neuron may have thousands of synaptic connections, each one representing something. Whether the information encoded in those connections survives cryopreservation, even careful vitrification, is a genuinely open scientific question. Some researchers argue the structural information is robust enough to survive. Others point to evidence that synaptic architecture changes at low temperatures in ways that are not fully reversible. The debate is not settled. What is settled is that we have never recovered a large mammalian brain from cryopreservation and verified that the information inside it was intact. We do not currently have a method to verify that even if we tried. Then there is the radiation problem, and it does not care at all about whether the crew is awake or asleep. A frozen crew is still a crew. They are still made of cells with DNA. Galactic cosmic rays do not check for consciousness before passing through. A high-energy particle moving through a dormant cell does the same damage it would do in an active one. It ionizes atoms, it breaks chemical bonds, it snaps DNA strands. The difference is that an active cell has repair mechanisms. Proteins move through the cell constantly, finding damage and fixing it. A hibernating animal runs these mechanisms at reduced speed. A vitrified human runs them not at all. Every cosmic ray event during a 40-year voyage accumulates in tissue that has no way to respond. By the time the ship reaches its destination and the crew is revived, if revival were possible, the radiation damage alone accumulated over 4 decades of dormancy in interstellar space would represent an enormous biological insult. The cancer burden would be severe. The neurological damage could be worse. These problems stack on each other. You cannot solve the ice crystal problem without solving the cryoprotectant distribution problem. You cannot solve the cryoprotectant problem at whole body scale without solving it at the brain scale, which is harder. You cannot solve any of the freezing problems and simultaneously solve the radiation problem, because the radiation problem does not care how well you froze the crew. And even if you solved everything else, you still need a revival process that works on a 37 trillion cell system that has never been successfully revived even after hours of cryopreservation, let alone decades. Suspended animation for interstellar travel is not a technology a few decades of biology will deliver. The problems go down to the level of what living cells are and how they work. General relativity does not forbid wormholes. That sentence is worth sitting with for a moment because it sounds like good news. It is not. The distinction between what the equations permit and what the universe actually provides turns out to be one of the cruelest gaps in all of theoretical physics, and wormholes sit squarely inside it. The concept emerged in 1935 when Albert Einstein and his colleague Nathan Rosen worked out that the field equations of general relativity contained a surprising solution. A black hole, those equations revealed, is not simply a point of infinite density sitting alone in space. It is connected, mathematically, to another region of space-time through what they called a bridge, an Einstein-Rosen bridge. The structure was real, not a metaphor, not a speculation, but a genuine geometric feature of the solution. 2 points in space-time, potentially separated by vast distances, joined by a throat. On paper, the shortcut humanity has always dreamed about was already there, embedded in the equations describing gravity itself. Then physicists looked at what those bridges actually do, and the answer was devastating. A natural Einstein-Rosen bridge, the kind that forms alongside a real black hole, collapses. Not slowly, not in a way that leaves room for engineering solutions. The throat pinches off faster than light itself could travel through it. You cannot use it. Nothing can. Even a photon, moving at the maximum speed the universe permits, cannot cross the bridge before it closes. The wormhole exists in the equations and is gone before anything real could take advantage of it. This is the first wall. The geometry is there, but the geometry does not wait. What physicists then asked was whether a different kind of wormhole might be possible. Not a natural one forming spontaneously near a collapsing star, but a constructed one, a traversable wormhole, something held open long enough for a ship to pass through. This is where the theory gets precise about what it would require, and the requirements are extraordinary. To hold a wormhole throat open against the tendency to collapse, you would need something that pushes outward against the geometry rather than pulling inward with it. Normal matter and energy always curve space-time in the same direction, inward toward concentration. Gravity pulls. To hold a wormhole open, you need something that curves space-time the opposite way, something with negative energy density. Physicists call this exotic matter. Exotic matter is not a substance waiting to be synthesized in a laboratory. It is not a material that exists somewhere in the universe and simply hasn't been collected yet. As far as any observation or experiment has ever determined, matter with genuine negative energy density does not exist in the natural world. Quantum field theory does permit one narrow, carefully constrained example. The Casimir effect, a measurable force between two uncharged metal plates placed extremely close together in a vacuum, involves a region of slightly negative energy density between the plates. This is real. It has been measured, but the scale is so small that calling it exotic matter in any useful sense is almost misleading. The negative energy produced between two plates separated by a nanometer is many orders of magnitude below what would be needed to stabilize any macroscopic structure. Holding open a wormhole throat large enough for even a small probe would require exotic matter with negative energy equivalent to the total mass energy of a large planet, in negative form. No known physical process produces anything close to this. The gap between what the Casimir effect offers and what a traversable wormhole demands is not a gap future experiments will close. It is a gap that reflects something fundamental about how energy behaves in this universe. There is a second problem layered underneath the first. Even setting aside the question of where the exotic matter comes from, traversable wormholes appear to be inherently unstable in ways that go beyond the throat collapse problem. Theoretical analyses suggest that any perturbation, any small fluctuation in the matter or energy passing through, would trigger a rapid collapse. The structure is not something you could stabilize and then use. The act of using it would likely destroy it. Stephen Hawking approached this from another direction with what he called the chronology protection conjecture. A traversable wormhole connecting 2 points in space also, under the right conditions, connects 2 points in time. This means a working wormhole would be a time machine. Hawking argued, and the mathematics supports the argument, that quantum effects would destroy any such structure the moment it was used for faster-than-light travel. Radiation would build up in feedback loops inside the wormhole, amplifying catastrophically, consuming the bridge before anything crossed it. The universe, it seems, enforces its own rules with considerable efficiency. What physicists are left with is a situation that is almost philosophically strange. The equations that describe gravity, tested to extraordinary precision, that predicted black holes decades before anyone observed one, contain wormhole solutions. Those solutions are real in the sense that the mathematics is consistent and correct. But the universe's physical contents, the actual matter and energy that exist, appear unable to create or maintain what the equations describe. The math says the door exists. The physics of what the universe is actually made of says you cannot build the key. This is not a closed question in the way that, say, perpetual motion is closed. Physicists still study wormhole theory. Papers are still published. The field equations still contain those solutions, and there is still legitimate work being done on whether quantum gravity effects, which no one fully understands yet, might change the picture. But the honest summary of where the science stands today is not encouraging. Every attempt to work out the engineering of a traversable wormhole runs into exotic matter, and exotic matter runs into the fact that the universe does not appear to make it in useful quantities. The physics that allows wormholes on paper also makes clear that building or stabilizing one requires resources the universe has not made available to anyone. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that seemed, for a moment, to have found a legal loophole in relativity. The idea was elegant. Special relativity says nothing with mass can move through space faster than light. Alcubierre's proposal did not argue with that. Instead, it asked a different question entirely. What if the ship did not move through space at all? What if space itself moved around the ship? General relativity already tells us that space is not a rigid backdrop. It bends, it curves, it stretches. Massive objects warp space-time around them. Alcubierre's metric took that flexibility seriously. His equations described a bubble of flat space-time surrounded by a region where space was compressed in front and stretched behind. The bubble would surf through the universe the way a wave carries a surfer, and the ship inside would never locally exceed the speed of light. It would just be sitting still while the geometry of space carried it forward. From the outside, the bubble could move faster than light. From the inside, nothing unusual was happening at all. On paper, Einstein's rules remained unbroken. The physics community did not laugh it off. This was not someone writing science fiction with equations attached. The math was legitimate. The solution to Einstein's field equations was real. For a brief period, warp drive shifted from science fiction to something physicists actually had to address seriously. That is a remarkable sentence to be able to write about anything. Then the problems arrived. They were severe. The first one looked familiar. Traversable wormholes required exotic matter, a substance with negative energy density that nothing in the known universe produces in useful quantities. The Alcubierre metric required the same thing. To warp space in the precise pattern the metric describes, you need matter that pushes outward gravitationally instead of pulling inward. Regular matter, every kind that has ever been detected or created, pulls. It curves space-time inward. Exotic matter would need to curve it outward, and no known particle does this. The Casimir effect produces tiny regions of negative energy density between two metal plates held close together. That much quantum field theory confirms. But the quantities are vanishingly small. They are nowhere near sufficient to stabilize a wormhole, and nowhere near sufficient to power a warp bubble. The original energy estimates for driving even a modest warp bubble were staggering. Alcubierre's initial calculations suggested the exotic matter requirement would be comparable in magnitude to the mass energy of the planet Jupiter. In negative form, Jupiter masses roughly 2 quadrillion times the mass of the International Space Station. The total amount of exotic matter ever confirmed to exist in any experimental setting would not register as a rounding error against that figure. Later work refined the geometry of the bubble, and some researchers argued the exotic matter requirement could be reduced significantly. Harold White at NASA pursued exactly this line of thinking for several years, and the work was taken seriously enough to receive institutional support. But reduced is not the same as achievable. Even optimistic refinement still demanded exotic matter in quantities that nothing in the known universe produces, by mechanisms that nothing in known physics provides. There is a second problem, and it cuts deeper than the energy numbers. If an Alcubierre drive could carry a ship faster than light from one point in space to another, special relativity implies it could also carry information backward in time. Not metaphorically, literally. A device that allows faster than light travel between 2 points in space can, under the right reference frames, be configured as a device for sending signals into the past. This is not a quirk of the math. It is a direct consequence of how relativity treats simultaneity. Faster than light travel is, from a relativistic standpoint, time travel. The paradoxes this creates are not merely philosophical puzzles. They represent deep inconsistencies in how cause and effect would operate. Physics resists this strongly enough that most physicists treat any proposed faster-than-light mechanism as almost certainly flawed, regardless of how clean the equations look. Then there is the control problem. The crew inside the warp bubble is causally isolated from the space ahead of the bubble. They cannot send signals forward. They cannot receive information from the direction they are traveling. This means they have no way to steer, no way to know what they are flying into, and no way to shut the drive off from inside once it has been activated. The bubble, once moving, can only be stopped from outside. There is no mechanism by which the crew participates in their own navigation. You would be sealed inside a moving region of space-time with no control over where it goes or when it stops. Some analyses of the Alcubierre metric suggest one more complication. As the bubble moves through space, the leading edge would sweep up particles and radiation. Hawking radiation may accumulate at the front of the bubble over the course of a journey, building toward dangerous and possibly catastrophic energy levels. When the bubble stops and that energy releases, the destination would receive it all at once. The ship's arrival would be its own destruction. None of this means Alcubierre's work was wasted. The paper produced years of serious theoretical investigation. It forced physicists to think carefully about what general relativity actually permits and why. It clarified how exotic matter behaves in curved space-time and why its absence matters so completely. That is genuinely valuable. But the investigation never produced a path to a working drive. It produced increasingly precise maps of why the drive cannot be built with anything the universe actually contains. The Alcubierre drive is not science fiction pretending to be physics. It is real physics pointing, very precisely, at things the universe appears not to contain. In 1950, the physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos and asked a question that has not been answered in the 75 years since. The question was simple: where is everybody? The universe is ancient, enormous, and by every statistical measure we can apply, almost certainly filled with planets that could support life. Fermi understood this. What he could not understand was the silence. If intelligent life is common, and if interstellar travel is achievable, the galaxy should be crawling with evidence of other civilizations. It isn't. That gap between expectation and observation is what astronomers and physicists now call the Fermi Paradox, and it turns out to be one of the most unsettling arguments against interstellar travel that exists. The numbers behind the paradox are worth sitting with. The Milky Way contains somewhere between 100 and 400 billion stars. A significant fraction of those stars have planets. Of those planets, a meaningful fraction orbit in the habitable zone where liquid water is possible. The universe has been running this experiment for 13.8 billion years. Earth itself is only about 4.5 billion years old, which means planets with the same basic conditions as ours have existed for billions of years before our sun even formed. If any civilization anywhere in the Milky Way developed interstellar travel even a few million years before us, they had an enormous head start. A few million years sounds like a long time. In cosmic terms, it is nothing. Here is where the math becomes uncomfortable. A civilization expanding through the galaxy at just 1% of the speed of light, stopping for thousands of years between jumps to build infrastructure and launch the next wave, could still fill the entire Milky Way in roughly 10 million years. 10 million years is less than 0.1% of the age of the universe. It is shorter than the time dinosaurs spent walking the Earth. If interstellar travel is achievable, any civilization with a modest head start should have reached every corner of this galaxy long before our sun ignited. Their ships, their probes, their automated von Neumann machines replicating themselves across star systems, some trace of all that should be detectable. We should be swimming in evidence. We are not. No megastructures orbiting distant stars. No transmissions on any frequency we have monitored for decades. No artifacts recovered anywhere in the solar system. No visitors. The sky is quiet in every direction we point an instrument. SETI has been scanning for signals since the 1960s and has heard nothing that survived scrutiny. The Kepler and James Webb telescopes have catalogued thousands of exoplanets and found no sign of engineering on any of them. The silence is not partial, it is total. There are many proposed explanations for this. Some researchers argue that life is simply rare, rarer than our intuitions suggest, and that we may be alone or nearly alone in the Milky Way. Others propose that civilizations inevitably destroy themselves before reaching interstellar capability, a grim hypothesis called the Great Filter. Some suggest that advanced civilizations deliberately go quiet or retreat inward into simulation or virtual existence and simply stop expanding. A few researchers have argued that we are not listening in the right way, or that the signatures of interstellar civilization are subtle enough that we have missed them. All of these explanations are possible, but one explanation fits the physics of this script precisely, and it requires no additional assumptions about alien psychology or self-destruction. If interstellar travel is effectively impossible for physical reasons, if the energy barriers, the radiation environment, the rocket equation, and the relativistic constraints all combine to make sustained expansion across stellar distances unachievable, then the silence makes immediate, complete sense. You don't need a great filter. You don't need civilizations that choose to go quiet. You just need a universe where the laws of physics prevent anyone from going anywhere. The galaxy would look exactly the way it does. This is not proof. It cannot be proof. Absence of evidence is not evidence of absence, and the history of science is full of signals that were missed for decades before anyone knew what to look for. But it is evidence. The Fermi Paradox is a data point arriving from a completely different direction than all the physics described earlier in this script, and it points at the same conclusion. Every line of reasoning, the energy requirements, the rocket equation, the interstellar medium, the relativistic limits, suggests that crossing the gulf between stars is not something a civilization eventually engineers its way through. Now the observable universe, silent across 13.8 billion years and 2 trillion galaxies, is offering the same answer from the outside. What makes this particularly striking is the timescale involved. We are not talking about a civilization that had a few centuries more than us. We are talking about civilizations that could have had millions or billions of years. The universe gave life every possible opportunity to spread. The distances were the same then as they are now. The speed of light was the same. The energy required to cross 4 light years was the same. And yet nothing crossed. Nothing arrived. Nothing built anything detectable anywhere we can see. That is a long time to fail to solve an engineering problem. It starts to look less like a problem waiting to be solved and more like a wall that doesn't move regardless of who is pushing on it. The universe is 13.8 billion years old, and it has been studiously, completely, and inexplicably quiet. And the most straightforward explanation for that silence is that the distance between stars is not a problem that gets solved. The human body is an extraordinary machine, but it was designed, in the most literal evolutionary sense, for a specific planet. Everything about human physiology, bone density, cardiovascular function, immune response, the pressure inside the skull, was shaped by roughly 3.8 billion years of evolution on Earth. 1 gravity, a magnetic field overhead, a thick atmosphere absorbing radiation. Remove those conditions, and the body does not adapt gracefully. It starts failing, systematically, in ways that compound over time and do not fully reverse. The most visible problem is bone. In microgravity, the human skeleton loses mass at roughly 1 to 2% per month. without aggressive countermeasures. The body reads the absence of mechanical load as a signal that dense bone is unnecessary, and it begins cannibalizing it. Astronauts returning from 6-month stays on the International Space Station already struggle to walk unaided. Their bones have thinned measurably. Their muscles have weakened. After a year in orbit, the recovery takes months of dedicated rehabilitation, and some losses never fully return. An interstellar voyage lasting decades would not leave a crew with compromised bones. It would leave them with bones that could shatter under their own body weight upon arrival, assuming they survived long enough to arrive anywhere. Muscle atrophy follows the same logic. Without gravity constantly pulling against the body, the muscular system has nothing meaningful to resist. The International Space Station crews exercise for roughly 2 hours every day, specifically to slow this process. They still lose muscle. On a voyage where every kilogram of equipment matters enormously, dedicating that kind of time and machinery to fighting the body's own deterioration is a serious operational burden. And exercise alone does not solve it, it slows it. The theoretical solution to microgravity is rotation. A rotating habitat generates centripetal acceleration that mimics gravity. This works in principle. The problem is the scale required for it to work without making the crew sick. Rotating a small compartment fast enough to simulate gravity produces significant Coriolis forces, the same effect that makes you dizzy when you spin. To keep Coriolis forces within tolerable limits, the rotation radius needs to be at least several hundred meters. That is not a spacecraft. That is a small city orbiting its own center. The mass and engineering complexity required for a rotating habitat of that scale feed directly back into every energy and fuel calculation that already makes interstellar travel seem impossible. You solve one problem, and the solution creates 3 more. The cardiovascular system has its own response to weightlessness. On Earth, the heart works constantly against gravity, pushing blood upward towards the brain. In microgravity, that demand disappears. The heart adapts. It becomes more efficient at doing less. Cardiac muscle weakens. Blood volume redistributes towards the upper body, which the body compensates for by shedding fluid overall. Return the crew to gravity, and the cardiovascular system is no longer capable of meeting the demand. The heart that has spent years in microgravity is not the same heart that entered the ship. Then there are the eyes. This one surprised NASA. Intracranial pressure rises in microgravity because fluid redistributes towards the head. Over months, this elevated pressure pushes against the back of the eyeballs, compressing the optic nerve and reshaping the eye itself. The result is progressive visual impairment. A significant fraction of long-duration ISS astronauts have returned with measurable changes to their vision. Some of those changes have not fully reversed. On a voyage of years or decades, crew members could arrive at their destination functionally blind. This is not a fixable problem with current medicine. The underlying mechanism, sustained fluid pressure against the optic nerve in the absence of gravity, does not have a pharmaceutical solution. The immune system behaves strangely in space as well. Latent viruses that the body normally keeps suppressed begin reactivating. The herpes family of viruses, which most adults carry dormant, shows increased reactivation rates in astronauts. Immune cell function changes in ways that are not fully understood. The system becomes less reliable at doing what it was built to do. In a sealed environment shared by a small crew over years or decades, With limited medical supplies and no ability to evacuate a critically ill crew member, immune dysregulation is not an inconvenience. It is a potentially mission-ending biological threat. What makes all of this especially difficult is the compounding. Each of these systems degrades in parallel. Bone loss, muscle atrophy, cardiovascular weakening, vision impairment, immune disruption. None of these happen in isolation. A crew member who has spent 3 years in microgravity is not dealing with one problem. They are dealing with every system in their body simultaneously operating below the level it was designed for. Physical therapy and exercise and careful nutrition can slow the deterioration. Nothing currently known can stop it. There is no engineering solution waiting in a laboratory that will make the human body comfortable in the deep space environment for the timescales interstellar travel demands. The issue is not that we have not built the right treadmill or the right supplement. The issue is that the body interprets the absence of Earth's conditions as damage, and it responds accordingly. The farther from those conditions a crew travels, and the longer they remain there, the more aggressively the body decompensates. Evolution spent billions of years solving for survival on one specific planet, at one specific gravity, under one specific radiation environment. It did not leave a margin for anything else. Biology does not care about the destination. It only knows what conditions it was built for, and interstellar space matches those conditions in almost no way at all. Set aside the physics for a moment, and the engineering, and the energy requirements. There is a barrier sitting underneath all of those that does not show up in equations. It shows up in human behavior, and the data on that behavior is not encouraging. Researchers have been running long-duration isolation studies for decades. Antarctic overwintering missions, where small crews spend 6 to 8 months locked inside stations during polar night, have become one of the most detailed records of what confinement does to a human mind. Submarine deployments offer another data set. So do analog missions like the Mars 500 project, in which 6 volunteers sealed themselves inside a Moscow facility for 520 days, simulating a round trip to Mars without ever leaving the ground. The findings across all of these environments converge on something consistent and uncomfortable. Depression rises. Interpersonal conflict escalates in ways that are predictable and difficult to prevent. Cognitive performance on tasks that require sustained attention begins to degrade. Sleep cycles drift. Motivation collapses in patterns that crews often cannot recognize in themselves even as they are happening. There is a specific phenomenon researchers have documented called the third quarter phenomenon. It is exactly what it sounds like. Roughly 3/4 of the way through a long mission, crews experience a measurable psychological crash. The initial energy of departure has long since faded. The end point is still distant enough that it offers no relief. Productivity drops. Conflict spikes. The emotional weight of confinement hits hardest precisely when the crew is most needed to perform. This has been observed in Antarctic stations. It has been observed in underwater habitats. It has been observed in simulated Mars missions. There is no reason to believe an interstellar crew would be immune to it, and every reason to believe the effect would be more severe. On any interstellar voyage, the isolation goes far beyond anything those studies have captured. The Mars 500 crew could send and receive messages from outside in something approaching real time. Antarctic researchers can call home. Even in the most remote environments humans have ever placed themselves, The rest of humanity was hours or days away in communication terms. On a voyage to Proxima Centauri, a signal back to Earth takes 4.24 years one way. There is no real-time communication, no news, no voices from home, no way to ask for help. If a crew member develops a serious psychological crisis, there is no one outside the ship to call. The crew handles it alone, with whatever expertise and stability it started with, which will itself have been degraded by years of isolation before the crisis arrives. The connection to Earth does not just fade, it severs. The civilization that built the ship, funded the mission, trained the crew, and cheered at launch is receding at the speed of light behind them. After a decade, everyone who knew the crew personally is older. Some are dead. After 2 decades, the world the crew remembers no longer exists in the same form. The mission duration breaks any psychological anchor to the home that sent them. This is not a problem that better communication hardware solves, because the problem is not the hardware. It is time. It is the irreversibility of departure. There is also the question of what the crew arrives to find. Suppose the mission succeeds in every technical sense. The ship reaches the Proxima Centauri system after 40 years of travel. What greets them matters enormously, and there is no guarantee it will be anything useful. Current data suggests Proxima b, the known planet in the habitable zone of Proxima Centauri, is bombarded by stellar flares from its host star at a rate that may render its surface biologically hostile. If the crew arrives after 4 decades of confinement to find a barren, irradiated rock with no life, no resources, and no future, the psychological weight of that outcome is almost impossible to calculate. There would be no return. There would be no second chance. There would be no justification to offer that could absorb 40 years of sacrifice. The ethics beneath all of this are unresolved and possibly unresolvable. An interstellar crew that launches does not only decide for itself. If the mission is long enough to require reproduction, children are born into it. Those children had no voice in the decision. They inherit a metal corridor and a mission they did not choose, and they will spend their entire lives inside it or die before it ends. The question of what kind of society that creates, what psychological damage accumulates across generations with no exit, no horizon, and no choice, is something philosophy is only beginning to frame. History does not offer many examples of closed societies under complete compulsion that remain psychologically stable over centuries. The examples it does offer are not hopeful. What the isolation research tells us, stripped of every optimistic assumption, is that human psychology was shaped by open environments, by social groups with exits, by the ability to leave situations that have become intolerable. Confinement removes that. Extended confinement removes it absolutely. The mind responds to that removal in predictable and damaging ways. Engineers can improve life support systems. They can design better lighting to preserve circadian rhythms. They can optimize schedules and rotate duties and build more comfortable quarters. What they cannot do is make the confinement stop being confinement, or make the void outside the hull stop being a void. Humans handle isolation and confinement poorly over months. It is difficult to construct a scenario where the same species handles it better over decades. There is one version of interstellar travel that the physics does not forbid, and it looks nothing like the science fiction version. No crew, no life support, no rotating habitat, no frozen passengers, No generation of children born into a metal corridor with no say in where they are going. The version of interstellar exploration that the laws of physics will actually permit involves a piece of electronics roughly the mass of a paperclip, moving at a significant fraction of the speed of light, with no ability to stop. That is the realistic picture. It is radically different from what most people imagine when they hear the phrase interstellar travel, and it is worth understanding exactly what it would and would not accomplish. In 2016, the physicist and entrepreneur Yuri Milner announced a project called Breakthrough Starshot, backed in part by Stephen Hawking. The concept was straightforward in outline and staggering in detail. A ground-based laser array, producing roughly 100 gigawatts of sustained output, would focus its beam on a sail made of an extraordinarily thin, reflective material. The sail, with its attached electronics, would weigh only a gram or two. The laser would push that sail for a matter of minutes, accelerating it to approximately 20% of the speed of light. At that point, the laser would stop. The sail would coast across interstellar space on its own, reaching the Alpha Centauri system in roughly 20 years. It would fly through that system in a matter of hours, collecting whatever data its instruments could gather, then beam that data back toward Earth. The signal, traveling at light speed, would take another 4.24 years to arrive. In total, roughly 25 years after launch, humanity could have its first close-up look at another star system. The physics of this is not in dispute. Photon pressure is real. Light sails work. The acceleration profile is consistent with known electromagnetic theory. What sits between the concept and the reality is a collection of engineering problems that are severe and in some cases may be beyond what current technology can approach. Consider the laser array alone. 100 gigawatts is roughly 10 times the output of the largest power plant ever built, sustained and directed with extraordinary precision at a target that is accelerating away from Earth at increasing speed. The beam has to stay focused on a sail measured in centimeters across distances that grow by thousands of miles per second. Pointing accuracy requirements are measured in fractions of an arc second. Any drift, any atmospheric distortion, any mechanical instability in the array, and the beam misses. The sail absorbs nothing. The probe goes nowhere. The sail itself presents a different class of problem. The material has to be thin enough to be pushed effectively by photon pressure, reflective enough not to absorb the laser energy and vaporize, and structurally strong enough not to shred under the acceleration forces. Those three requirements pull against each other in ways that no existing material satisfies simultaneously. Researchers have proposed candidates, none of which currently exist in manufacturable form at the required specifications. Then there is the Interstellar Medium. A gram-scale probe traveling at 20% of light speed hits hydrogen atoms with considerable energy. Over 4.2 light-years, the cumulative effect on a centimeter-scale sail and its attached electronics is not negligible. The probe has to survive this environment with no shielding to spare, no redundancy in mass, and no ability to repair itself. Suppose all of that is solved. The probe arrives. It flies through the Alpha Centauri system at 20% of light speed, covering the distance between the inner and outer edges of a typical star system in somewhere between a few hours and a day. There is no slowing down. There is no orbital insertion. Whatever the cameras and sensors can capture during that flyby is all there will ever be. No follow-up pass. No hovering over an interesting feature. No collecting a rock. The probe is gone from the system before the first image is fully recorded. the data rate coming back would be tiny. Power on a gram-scale probe is measured in milliwatts. Transmitting across 4.24 light-years on milliwatts produces a signal so faint that detecting it would require radio telescopes larger than anything currently built. Estimates suggest the data rate could be just a few bits per second under optimistic assumptions. A single low-resolution image might take days to transmit. The entire scientific return from the mission could fit in a small file. This is not nothing. A blurry image of a planet orbiting another star, taken from a few million miles rather than 25 trillion, would be one of the most significant scientific events in human history. Spectroscopic data from that system's atmosphere, even crude measurements of its magnetic field or radiation environment, would tell us things no telescope on Earth or in Earth orbit can reveal. The case for breakthrough starshot, or something like it, is real. Other concepts exist at varying distances from practicality. Nuclear-powered probes using existing fission technology could potentially reach a few tenths of a percent of light speed, meaning travel times to Proxima Centauri measured in thousands of years. These are not missions that anyone alive today would see completed. Von Neumann probes, which would self-replicate at the destination using locally available materials, represent a theoretically elegant solution to the scale problem. But the technology required to build a self-replicating robotic system, robust enough to operate autonomously for centuries in a foreign star system, is far beyond anything currently imaginable. The honest line is this: robotic probes with no deceleration requirement, carrying no biological passengers, are something the laws of physics will allow. Crude interstellar missions are not. The difference between a gram of sensors flying past a star and a human being arriving at one is not a difference in degree. It is a difference in kind, in scale, in everything that matters about what it means to go somewhere. Sending a gram of electronics to flash past another star is not the same thing as going there, and the gap between those two things is where most of humanity's interstellar dreams actually live. Every barrier described in this script is real, and none of them are waiting for a clever engineer to come along and quietly remove them. That is the thing worth sitting with. When the steam engine was too slow, someone built a faster one. When copper wire couldn't carry enough signal, someone switched to fiber. The history of human technology reads like a long argument with inconvenience, and inconvenience has almost always lost. But the barriers between us and the stars are not inconveniences. They are not engineering gaps. They are consequences, hard, precise, mathematical consequences of how the universe is structured at its most fundamental level. Take the speed of light. It is not a speed record waiting to be broken by a better engine. It is a feature of space-time geometry. Mass cannot reach it because the equations governing space-time say that accelerating mass requires energy proportional to a factor that climbs toward infinity as you approach the limit. This is not a wall you can redesign around. The wall is the shape of space itself. Engineers did not build that wall. No physicist discovered it and left a gap for future researchers to exploit. It was there before the first atom formed. The energy requirement follows directly from that. You need energy to accelerate mass. The faster you want to go, the more energy each additional increment of speed demands. The rocket equation is not a problem of clever design. It is a consequence of momentum conservation, which is one of the most tested laws in all of science. Nobody has ever found a loophole in momentum conservation. Every gram of propellant you add to the ship is a gram that itself must be accelerated, which demands more propellant, which demands more energy, and the numbers spiral upward in a way that does not care how sophisticated your engineering team is. Then the barriers start talking to each other. That is the part that is genuinely strange. Solve the energy problem somehow. Push the ship to a meaningful fraction of light speed, and the interstellar medium, that near-empty scattering of hydrogen atoms and dust that seems like almost nothing at slow speeds, becomes a continuous particle accelerator pointed directly at your hull. Every hydrogen atom your ship strikes at 20% of light speed carries the energy of a fast proton in a collider. You cannot outrun this. The faster you go, the worse it gets. The solution to the distance problem makes the radiation problem lethal. The solution to the radiation problem demands shielding mass. The shielding mass feeds directly back into the rocket equation. Round and round, wormholes require exotic matter with negative energy density. The universe does not appear to make exotic matter in macroscopic quantities. Warp drives require the same thing, plus causality problems that special relativity does not gracefully absorb. These are not proposals waiting for better materials science. They require things the universe seems not to have put here. Suspended animation runs into ice crystal formation at the cellular level, and into the fact that a frozen crew accumulates radiation damage with no biological repair mechanisms running to fix it. Generation ships run into genetic bottlenecks, social collapse, and the quiet ethical problem of conscripting people into a mission they never agreed to take. Each proposal, examined closely, opens into a different room of the same building. The rooms all connect. This is what makes the barriers feel different from ordinary engineering problems. Ordinary engineering problems have workarounds. If one material fails, you try another. If one trajectory is inefficient, you compute a better one. But here, the workarounds lead back to the original constraints. There is no sequence of steps that adds up to a clean solution, because the constraints are not separate obstacles arranged in a line. They are facets of the same underlying geometry. The universe was built at a scale where the distances between stars are measured in years of light travel, and the laws governing energy, mass, and space-time make crossing those distances something that biology, operating on biological timescales, cannot do. Consider what that actually means. The nearest star to our Sun is 25 trillion miles away. Our fastest spacecraft, moving at roughly 38,000 miles per hour, would need 73,000 years to reach it. To cut that to a human lifetime, you need speed so high that the energy required exceeds everything humanity has ever produced. And even if you reached those speeds, the radiation environment would kill an unshielded crew within days. The shielding would make the fuel requirements impossible, and time dilation would ensure that everyone you left behind on Earth aged and died while you were still in transit. The physics does not leave a gap. It closes every door in sequence. There is something almost deliberate about that. Not deliberate in any intentional sense, but systematic in a way that feels, when you trace it carefully, like a unified answer rather than a collection of separate bad news. The speed of light limit, the energy scaling, the rocket equation, the interstellar medium, the radiation, the biological fragility, the psychological limits, these are not independent misfortunes stacked against us by chance. They all emerge from the same source, the laws of physics applied to the specific scale at which the universe placed its stars. The gaps between stellar systems are not accidentally the size they are. Gravity, nuclear physics, and stellar evolution conspired to produce stars spaced light years apart. The same physics that makes stars shine makes the distances between them crushing. What this suggests, and it is not a comfortable suggestion, is that biological life is local by nature, not local the way we are local to our continent or our planet. Local to our solar system in a way that may not be escapable regardless of how much time passes or how sophisticated our civilization becomes. The Fermi Paradox has been sitting quietly in the background of this entire conversation. The universe is 13.8 billion years old. It contains trillions of galaxies and hundreds of billions of stars in ours alone. If interstellar travel were achievable by sufficiently advanced civilizations, the Milky Way should already be full of evidence that someone did it. It is not. The silence is not proof, but it is consistent. It fits a universe where the barriers are real. None of this means there is nothing to do. Robotic probes, laser sails, gram-scale spacecraft flung toward Alpha Centauri at 20% of light speed. These things the physics permits. We could have close-up images of another star system within a generation if the engineering problems were solved. That is not nothing. That is extraordinary. Even if it is not the interstellar civilization the science fiction imagined, the machines can go where the biology cannot. But it is worth being clear about what that means. Sending a signal to another star or a chip the size of a fingernail is not the same thing as going there. The dream that drove a century of space enthusiasm was a human dream. Crews, colonies, civilizations spread across the stars, the species becoming something larger than one small world. That dream runs directly into the structure of reality. Not the current state of technology, the structure of reality. The speed of light is not a current record. The energy requirements are not a current limitation. They are permanent features of a universe that did not design itself around what any particular species on any particular planet would prefer. The universe built the barrier the same way it built everything else, out of the laws of physics, at a scale that makes no allowance for what any one species on any one planet happens to want.